Hi, my name is Pablo Galindo.
And my name is Łukasz Langa.
And this is the Core.py podcast, an established podcast where we discuss internals of CPYTHON and our adventures in making a new version of your favorite programming language. Now, the 2025 edition, in which we basically lost an entire month and we disappeared for the whole December for weird reasons. What are the reasons, Łukasz? Why we disappear? Why we do this every single time?
Well, there's reasons, personal and otherwise. But the funniest thing is how every time it happens, the last thing I say before is like, yeah, see you in 2 weeks. And then it's like 2 months.
Well, maybe we should just embrace this and say see you in 2 months.
Especially that we want to actually do like a part 2 of a 3-part thing right now, which is talking about memory management in Python. We covered memory allocation first, and now we're going to be talking about reference counting. And in a future episode, we're going to cover garbage collection, which makes zero sense to start with. Everybody wants us to talk about garbage collection, but we thought, You know what? You need to explain all the things that make garbage collection actually tick, which memory allocation we already did, or you no longer remember, right? Because it was 2 months ago. But
maybe people can go back to the episode.
Yeah, we did cover that.
Right. I mean, we did this poll, I think, somewhere, and like in the Spotify and like X or the new 300 new social networks that we have between December and now. And everybody wanted garbage collection, it's by far. But we said, you know what? Let's not. Let's start with this other thing. And you will say, but Pablo, this is very boring. Everybody knows reference counting. Well, sure, but we like to do 2-hour episodes. And you may say, do you have 2 hours for reference counting? My answer will be, you will be fucking surprised if we have 2 hours. We certainly have 2 hours, but we also have like 6 kilotons of what happened between the end of November and now. And certainly that will guarantee more than 2 hours. So we are going to keep this funny and simple. But there is a lot of meat here that we could go.
Right. Reference counting is this thing where people are like almost embarrassed that Python is doing this, because everybody on their computer science classes learns that reference counting was like super popular back in the day. But today, nobody designs a language and says like, hey, I'm going to be doing reference counting. It sounds like a technique that is out of date, especially with multi-core processors and everything. But it turns out that like if you have an iPhone or a Mac, like that system is doing reference counting as you speak, as you're listening to us right now. Like there's reference counting happening there all the time. So it turns out like maybe it's not universally applauded, but it is very much in use.
Not only that.
And if you're using Python, yeah, very much so.
Right. And not only that, like several CPU architectures have instructions particularly tuned for reference count. Like there was this article that I think we checked like 1 year ago talking about how one of the big changes in like the new Apple Silicons is that the instruction set like handles slightly better than just the AR64 vanilla version Swift automatic reference counting. So people are investing quite a lot in the hardware also to support the model.
Yeah, maybe that explains how Python on M1 processors is indeed like quite much faster. When I run my old MacBook Pro and run the test suite compared to the M1 Mac, like it's night and day difference how much slower it is on Intel than on M1.
Oh, but that's because of all the Bitcoin mining. You should have deactivated. You should have deactivated the Intel Bitcoin mining advanced utility. Intel loves to add those.
Right. Before we get to reference counting, I learned 2 important things that I think all our listeners should know. So first of all, Carl Meyer's hockey team, the Bellingham High Sticks, are currently in the top 2 of their league.
What?
Yeah.
Top 2?
Carl himself scored a goal on Friday in a game they won 8-3. So super impressive. Go High Sticks.
Wow. Go High Sticks. Very impressive.
Indeed.
Okay.
And then the second thing is we usually call Brand Justin on the podcast because he told us when he was a guest that like it would be great if we just had at least one episode where we don't call him by name.
Right.
So he said Justin. But it turns out if you go to GitHub and you go to Brand's profile page, There's a repo called Brand Booker on the Brand Booker account. So it turns out that Brand is not indeed, in fact, Brand's first name.
What is the name?
Brand's first name is Gary.
What?
Yes. It's like,
no.
I have never heard that before, but somebody said like, hey, you mean Gary? And I'm like, Gary who? Like, it's like, no, like it says on...
He's trolling us, or is
I don't know
like real?
if this is real or not. I have very little like images in my head when I hear the word Gary. Honestly, the only one is a very weird reference. In Fallout 3, there was this weird quest where you go inside some vault, and in this vault, there's 50 clones of this guy, Gary. So like every person in the vault is called Gary.
I remember that one is fantastic.
Yeah.
But yeah, in LinkedIn, it's also Brand Booker. I don't know. Looks suspicious.
There's a repo.
No, I have it. Yes, okay. And the about of that repo says Gary Brand Booker second.
Yes. So it's public, which is why I don't feel like I'm like, kind of really breaching any secrets there. But it is a tidbit I never knew.
That's kind of interesting.
Yeah.
So let's call him Gary for now.
I wouldn't, right? I mean, like, Justin is weird, and it's sort of in reference to the JIT, whereas Gary is a name that he was given, and he chooses to call himself Brand. So
but he put that in his Brand Booker repo.
That's interesting, right? So, but there's clearly something more there. So we need to actually ask. We need to reach out and say like, hey, like, can we?
Okay, we'll let you reach. Yes. Let's ask. Let's be nice.
We want to just like,
don't be assholes.
Yeah.
Well, anyway, do you know what is not called Gary? Reference counting. Wow, what a segue! Incredible.
Fantastic skills.
Great skill.
Narration.
I'm almost like 38 degrees Celsius of fever right now, so pardon my segue skills. Anyway, it's cool. So why reference counting? Is this like a model that is interesting for programming languages? But not only that has consequences on how people interact with objects. For instance, if you have different semantics than Python has. For instance, let's say you have C++, when the semantics of Python passing arguments to functions is passed by value by default, unless you use reference or pointers or whatever it is, then you copy, right? So there is no reference counting, it's just raw memory over there. But like the moment you have reference counting, it means that probably your semantics are going to be slightly different. Actually, Python obviously has, well, it has, I don't know, man, like people like to discuss this quite a lot. They say, oh no, it's not passed by reference or passed by value, it's passed by name.
Yes. So like before we get to this, I was just really thinking about what you like explained in different words, which is what was first, whether Guido came up with his idea for the semantics of Python, or whether the chosen technology of getting there, of getting like a runtime going, informed what was possible in Python.
Okay.
Right? Like, you know what I mean?
New segment of 2025 is bets.
Bets.
Which is totally legal. Okay. We don't know the answer of this. Like, we don't know what came first, right? Like, we have no idea. Is that right, Gukesh Lange?
It is.
Okay. So, but we have access to Guido. It's easy. We can just check. So, we are going to bet, and we are going to unveil the truth in the next episode. So, I bet you that first it was the reference count and then the semantics. Like, he chose reference count before he chose the semantics of passing by value.
I believe this.
Do you agree, or do you want to bet otherwise?
Now it would only make sense for the drama, right? For the episode. If I say, yeah, okay, like it makes perfect sense, but
yes, we need
I'm going to play the devil's advocate and say that
you will lose.
Reference counting was chosen because it fit the idea for the language.
Okay. So we will ask Guido, and we will tell in the next episode, and the person who loses needs to say, I was wrong and you were right.
Fine. That sounds fair.
In front of our thousands of listeners.
Yeah. But since we don't know
impressive.
in this episode, like I'm free to just say like I was really wondering about this.
Yeah.
Because reference counting really does inform how things connect later on.
It's so tightly coupled that it's actually very difficult to guess. Like I can imagine Guido saying like, oh, I like to pass pointers, it's easier. Like I don't want like pass by value is just stupid. Like in the sense that it just now adds this extra layer of cognitive load to all your users, because like now by default you do the expensive thing, right? And like if you want a language that is very easy for newcomers and like you don't need to teach a lot of concepts, copying every single stuff that you pass is not great. And now you need to introduce the concept of some interaction, like references or pointers, and like you need to tell the difference, right? While the Python model is kind of like half curse, like in the sense that it's not technically pass by reference, because like, you know, it has all these things, and like it's the people like to teach it with the box. You know, there is a box and I have the box here and I pass the box and the contents of whatever. I mean, a lot of educators have put a lot of effort to make this understandable. But even if you don't know the real model, like you can have an intuition easily. You know, I have the thing and I pass you the thing, and now you have the thing. Like there is no copy. Like, no, it's copy. Like in C++, even very experienced programmer have the problem where like, oh, you forgot the reference. Now your vector of 6 million elements is being copied. Whoopsie. And it's just one character, dude. It's a character. It's like the ampersand. If you don't have the ampersand, you can have cons b. And now it's like, but it was not a reference. It was a vector. And like now your program is slow for no reason. So that is probably, maybe we don't want the easy mode. You know, like Swift has like a similar model, like with some caveats and whatnot, and it's in the type system as well. But yeah, maybe I guess it was probably the model. I don't know. Like it's difficult to guess.
Right. Like the entire idea for reference counting mostly comes from this sort of realization that, like, even though we talked about memory allocation in episode 16, remember? That meant that you need to ask for memory when you need it, and then you need to free it, so give it back when you no longer need it. And doing this manually is cumbersome and hard to do right.
And also,
which many users of C and C++ will tell you.
Illegal is illegal. It's illegal. If you do it, it's illegal, right, according to the White House.
Exactly. So, you know, now like we need to automate this. We have computers to automate this. So
memory safety.
We don't even have like this choice, like, you know, whether to do it or not, because Python programmers don't think about explicit memory management, right? Python, when you create a new object, there's going to be memory for it. You don't have to think about it. And when the object is no longer accessible, no longer reachable, it disappears. So
I mean, it would be so nice if that were fully true. I mean, it's mostly true, but you know, like stating that, imagine that someone makes one of these clips of Gukas Langa saying Python programmers don't think about memory management at all, like and people with their TensorFlow bullshit, like using 70 terabytes of memory or RAM because they forgot some garbage collector or some weird C extension.
Yeah, most of the time, because obviously as the maintainer of a memory profiler, you know full well that a tool like this is necessary. And why is it necessary? Because like
use memory today. Yes.
Things get complicated, even if the intended ergonomy of it like is to be easy to use. Sure, it is easy to use, but it's also possible to misuse.
Right.
Which is why we are spending 3 episodes talking about memory management. Like if it was fully like trivial, there would not be any material. But we do have a lot of it. And reference counting seems to be the easiest part of that, but there's a lot of things to cover, honestly.
Just one last thing before we continue with this. People that still complain that reference count is stupid. Reference count, even today, if you grab any C++ big code base, is normally the biggest memory management mechanism that people tend to use. Like there was this talk that Brandon Rhodes made at some CPYTHON long ago, showing the use of shared pointers in code bases over time. I don't know what code bases he chose, maybe some Google stuff, maybe TensorFlow or something like that. And he was showing how the amount of variables that were shared pointers were growing and growing and growing over time. So he had this like very interesting and provocative thought to say, especially in a CPYTHON, that it was like Python is the limit of C++ at the end, like, so you start with like, close to the metal kind of thing, and then you get with 6 trillion shared pointers, and then you get Python, so Python is the limit of C++, according to Brandon Rhodes. But it's very interesting because like that is when you have this kind of ownership, schemas, like having reference count is the easiest way to solve it and to not go crazy. Because you need to think, like, one of the problems with Rust is that you really need to think about who owns what, and like the moment you have like data structures that can loop, like graph or trees or double linked lists or whatever. I mean, who needs double linked links in Rust? Maybe, but like but graphs, sure, like that you need graphs, and like everybody's like, oh man, how do you implement that tree in Rust? Like, it's impossible. Like, blah, blah, blah. And then you get all this like weird thing with like double pointers and boxes in pointers and boxes, and like, no, dude, like just use a thing.
Yeah, I mean, like in Rust, the problem becomes very apparent very quickly when you have, for example, I don't know, a game. There's a simple game, and there's a few characters that are on the screen, and the characters can impact each other somehow, right? And you need to calculate those like interactions both ways. Like
I was thinking about two characters like B and C. And like, I was like, okay, two characters that like they can impact themselves. Like, you mean like actual people?
Yeah. I mean, like, kind of the objects that represent some like NPCs or players or whatnot.
Yeah.
Like,
got it.
If you have more than two, and suddenly there's a double for loop, suddenly things become very complicated if you didn't think it through, designing it beforehand.
Right.
So like, you can make it extremely fast, but things can be also pretty non-ergonomic, which is why like Rust is still like running this website, or like, are we game yet, which is like whether you can actually write games in Rust. And like last time I checked
carefully, the Rust community will invoke the secret commands of annihilating our views of skill issue.
So like you definitely can, but there's just some practical issues.
Okay, this is what I think. Okay, this is my view of the whole thing, which, by the way, I program in Rust. Like, I'm not a detractor of the language or anything, but this is my insight. When you first look about how the hell you implement graphs or trees in Rust, and then you get to these websites that compare like 5 different ways, and like, with all the different approaches and whatnot, I actually check how they are implemented in the standard library, and most of the tree like data structures are implemented with unsafe because guess what? It's much easier to have like some small unsafe code just to have like actual pointers in the middle, and just sacrifice a bit that the kind of like it's very little code, you can sanitize it, blah blah blah. But like it's not this unsafe is for is evil, right? Like, so at the end, like the having some form of like kind of share ownership under the rug is still a good trade-off to not go crazy.
Right.
But we are not talking about Rust. We are talking about Python. so let's go back to the
reference counting. Let's talk about that then.
Okay. So in Python, variables are basically names, right? Which is very easy to say, but it has interesting consequences. So those names basically will have references, and those references will be incremented on certain operations. For instance, the easier one is like when you assign to the name. So you say like, x equal Pablo. And then Pablo is a string that is living somewhere in the memory of the program and has a name, is x. But you can also say y equal x. And in other languages that will create a copy, but in Python just has now 2 names. So the string Pablo has the name X and the name Y. Quite simple. Mm-hmm. But also like, there is other tricky things. And many people say, oh, this is obvious. But like, when you start actually hacking the interpreter, at least for me, I always need to think about this. Like, is this increasing the reference? For instance, when you pass an argument to a function, you increase the reference count. But like when you are calling the function in C, you don't do it. Like that happens for you. So, but you need to know that like, obviously, across the lifetime of the function, the argument is alive. Yes. Because obviously, someone can drop it meanwhile you're running. But like in the trickier cases, sometimes you need to think about it because like, you start like managing references in the function and thinking about what is going to happen when it finishes. Like I always need to think about to not get crazy. For instance, one example of this, function returns. Like when you return from a function, in theory, you should return with a reference count that you're going to transfer.
Fresh, yeah.
Classic move of not doing it correctly when you code in C. So this is just coding in C, not in Python. In Python happens automatically. But when you code in C and then you return the known object, most people just return known. Mm-hmm. They say return PyNown, which is a singleton, right? But you in theory, you need to increase the reference count before returning because otherwise you're not transferring the ownership, right? But it can also happen, especially this is the most common case, when you put objects in collections. Like you put the string Pablo, you put it in a list and now it has another name which is implicit. It's just an element of the list, like the element 3. And then this reference can be decreased when those scopes are closing. For instance, when the function returns, or when you delete explicitly the name, or when you remove the object from the collection. And the method is like the algorithm is very simple. Once the number of names or references reaches 0, then it's safe to remove the object, and then you can just clean the memory, or at least tell the allocator that you don't need it anymore, which may not actually do anything.
Right. So in Python, when you're writing code, end user code in Python, you don't really think about it that way. But when you see a C extension, or you maintain Python itself, you're going to be thinking of references as either owned, which is the kind of reference that you get in Python code by default, which is this reference is mine. If there are multiple ones, there's going to be many of them. And there's really very little in terms of optimization that you can do as a Python programmer there. There's a reference, that's what you're getting.
Right.
In C, there's nothing stopping you from breaking the law and not increasing a reference when you're returning from a function and just sending the value that you had. That's invalid. But sometimes you are getting a value like that,
right,
that you know that the reference count was not increased, but you know that the function that you're in right now is short-lived and is not going to do anything, so it's just more efficient to skip that increase of the references, which is now called a borrowed reference. So there are functions in Python and the API that return borrowed references.
Question. Which is the most common function that returns a borrowed reference and creates all the bugs?
Oh, so that's the dictionary one, like getting the...
Yes, predict get item.
Yes, exactly.
Predict get item is returning a borrowed reference. And everybody gets wrong.
Yes, exactly. But like we got a better API now thanks to free threading. We need this now.
No, that was Victor Stinner, no? No, that was another problem. Sorry. Predict get item with error, I think maybe still borrow. That was because also predict get item eats the errors.
Yes, yeah.
Yes, beautiful. Okay, but maybe there is another one for free threading right now.
Yeah, I think get item ref.
Get item ref.
Yeah.
Yes, that's the classic one. So you see by get item,
right?
Evil.
Yeah. So, but at least borrowed references are documented as such
most of the time.
So you also have a third way of just writing some code where you're skipping all of this because you're just assuming that you're a god of memory management and you're not going to make any errors.
Tier 4.
Yeah, so you can steal references, which is like you just
which is the common API that steals references. Doubles. By double set item steals.
Right.
By for instance, by list append increases.
Yes, list append.
List append. By doubles, you end with an empty tuple, and then you're supposed to put something that already is alive and steals. Which is also the most common way to leak, because most people increase it and set it. And then you leak. A classic.
Right. So let's talk about how you can check whether you have many or few references to an object.
Yes, you can and you shouldn't use this function for anything. If you find yourself using this in actual code, just run. Something wrong is going to happen. You don't like that. But you can check how many references an object has uses sys.getrefcount. But the number will be weird. Why it will be weird, Gukish?
It's gonna be too high.
How much higher?
2.
2 higher? No, it's 1 higher, no?
No, it's 2
No,
higher.
No, it's 1. Okay. Who is right? I think I am. How can it be 2 higher? No. Python, no, it's 1 higher.
Oh, 1 higher. Like it says 2. Right?
Yes. Of course. Yeah, of course. How is 2 higher? No. I was completely wrong.
Okay.
You were wrong.
I was wrong. And Pablo was right.
Yes, exactly. Yes. That's what I wanted. That's what I wanted. Thanks. I can go to bed now. Happy. Okay, so it's 1 higher. But why, Lucas? Why is 1 higher?
Well, because there's an additional reference while you are looking at the object.
Yes.
When you are passing the object, by passing it, there's 1 more reference.
I hate it. I always thought like we should just subtract 1, dude. Like I can understand why this is a possible answer. You know, like at the time I'm checking how many references does it have, and obviously it's 2. But that's not what the function is supposed to do. The function is supposed to say, I have this object. How many references there are? Of course, when you check, there is 1 less. Sure, yes. But that sounds something that Pedantic Pablo will say. You know, like it would say, actually, it will be 2. No, dude, like just report 1. Because like, do you know what? Now, everybody that actually uses this function for something, which remember, you shouldn't, is subtracting 1.
Yes.
Because like, you know, like you actually want the number, not the stupid like, haha.
Yeah.
one
but
more.
we cannot fix it ever now because everybody's subtracting
Yes.
1. So if you fixed it,
minus 1, minus 1.
Yeah, it would be 0. Yeah, so in any case, there's GetRefCount, but there's also better one that can tell you everything. But that's only if you have a debug build of Python.
Pedantic Pablo has something to say.
Yeah.
Ha! Like you were slightly right. What about that? You were slightly right, but it's not 2. It can either be 1 more or a facton more. Because if you check sys.getrefcount of none, then you get like the Immortal refcount number. Oh no. And that is very big. I don't think we are trimming that. Probably you're getting like some stupid ginormous number.
No, it's just 32 bits, honestly. It's just 4 billion. It's like, it's not even that big.
But sure, but like is not the real reference count, right?
Oh yeah. Yes, we're just abusing that.
It's just but you get the bullshit number. You don't get the real number trim. Okay. So you can get 1 more or a factor more.
Yes.
Okay, so the back builds. Yes. There is sys.gettotalrefcount. And that is very cool because that tells you all like the sum of the ref count of all the objects. And you will say, that's stupid. Why would you like that? And it's mostly stupid, but it's very useful for what?
For running the same thing multiple times.
I mean, sure, but you can call the function 3 times and you don't need total get ref count to call the function 3 times, right?
No, but like if you check before calling the function, then you call the function, you see, oh, there's more references. You call it again, and then you see there's more references.
Right.
You call it again, which is like...
It's a leak checker, right?
This is more of an art than a science. Because obviously, normal code will set up some caches, right? Like it's going to have some global state and whatnot.
Dude, that's evil. That's evil. All the code in the world set up weird caches.
Yes.
Like you will say, certainly that's like 1 or 2 things to know, dude. Like
everything.
Like the first time you call a function, a bunch of bullshit happens. Like things are being created, the frames, blah, blah, blah. Like sometimes there is things like it's just random. It's just random. Like, you think this is deterministic? It's not fucking deterministic. It's just random shit. Yes. So
yeah.
Yeah.
Yes. Which is why, like, most of the time you need to run at least 3 times to get any reproducible reference count. And why are we doing this? To find whether either on the interpreter side or in a C extension, we did something wrong with the manual increases and decreases of references, and therefore have memory leaks, which we call reference leaks, ref leaks.
Ref leaks, and that's the bane of our existence.
It is.
All the time. Because like this ref leak can happen because you forget to decrease a reference count, so you never decrease it, so it's always alive, and every time you call a function there is 1 more and then 1 more. But also can happen because while objects are surviving your function even if they get eventually destroyed, right? So for instance, if you have a global list, you call a function and then you append to that global list, before the interpreter finishes, that list is going to be destroyed. So it's not technically a leak in the lifetime of the interpreter, but it's a leak in the lifetime of the function. And you will say, duh. But like, do you know what? This happens very sneakily. Like for instance, do you know that if you raise a warning, that happens because there is like a global bullshit warning list that blah, 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 blah. So raising a warning, it does. In PyTest, so if you try to implement something like this in PyTest, you will discover that every single time you log, the log string goes to some global list. Why? Because then PyTest can hold that log until the test finishes, see if it fails, and only if it fails, then it will show you the logs, right? Because like it's trying to be super helpful. But that means that every time you log, then technically you're leaking. So and this happens all the time. Like this is one of the most tricky things to teach people contributing to CPYTHON, and they get these errors because sometimes it's not really a ref leak in the sense that you forgot a PyTest ref somewhere. It's because you put like classic one, right? Like you import a module in the function, and like that creates a bunch of state, and like the state that doesn't go away.
There's a bunch of modules that just have some implicit state like caches and so on.
Right.
So literally in regression tests, we have ways to reset the state.
That code is coarse, dude. Like Victor Steiner is a hero. He wrote the first version of this, like runs the function in the test suite like a stupid amount of times.
Yeah.
By the way, it has the funkiest syntax in the planet. You know, like it's number of warm-ups colon number of actual repetitions, and like it looks very funky the first time you see it.
Yes.
But
especially that you can actually just not specify the numbers, right?
Right.
Because
yes. Just a column.
defaults. So you can just say like dash uppercase R colon. Yes.
But you need a space between the R and the colon, otherwise it's weird. So yes, but that code is weird, man. Like it needs to reset all the caches. Like for instance, all the ABC caches. Like when you check each instance of this and that is cache, because that is a very slow check. You know, like you need to check, oh, is this class a subclass of the class, blah, 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 blah. Like that takes a lot. You need to compute the MROs, and MROs is using the C3 linearization algorithm. A lot of computer science there, which Łukasz knows a lot because he implemented one version of that.
Yeah, I implemented that for single dispatch.
Very cool, but it's also very slow. And
because it's in Python, but like you can actually see the implementation in Python.
No, I mean, even the C version is slow. Like its instance is surprisingly slow in general without the caches. Right. So we cache
it. It is also slow because it is very hackable, right? You can just essentially hook into its instance and say, I'm just going to claim that I'm an instance of this class, whether I'm not.
In so many ways, exactly.
So yeah, like its instance actually supports all of this, which is dynamic.
But it's also like super coarse because you can do it by function. So you implement its instance check, but you can also do it by the ABC module, which is like, that is weird that you have a module and you say, oh, register. And like the C code that needs to reach into the ABC module internal just to check if the class is in the register list. That's bananas. But yes, that is very useful. But also, apart from most people know this, like, well, at least it's slightly known. But there is also this other cool mode called TraceRefs, which was the default until Victor Steiner started to kill it, and now we may kill it in the next version because it's not that useful. Although I still use it, please don't kill it. but you know what this does? This with TraceRefs. So this is a mode where you need to pass when you compile Python. You need to compile Python in this mode, because it's lower.
Yeah, so like you get the reference counts, but you also see where the references are increased.
No, exactly. With TraceRefs, that would be cool, right? But no, the name may be suggesting that is that, but it's not. That would be very cool. Now, with TraceRefs, what it's doing is that it gives you a list of all the objects that are alive. So total ref count tells you like there is 6,000 reference counts, but with TraceRefs unblocks a new API called sys.getObjects, and that returns a list of all the objects in existence. So because why? Because one of the problems of the total ref count is that it doesn't tell you what is being leaked. It just tells you, oh, I run the function and there is 3, and then I run it 600 times more, and then there is 12. And it's like, okay, so what is being leaked? Haha. Why do you want to know that? Haha. Greetings. So with get objects, you can actually do the same check, but with the objects themselves, which is very slow, by the way, because you need to like go around. And then there is like some trickiness because just creating the list of objects adds more objects. Obviously, the list is an object now and it needs to be there. So it's just a bit tricky, but you can technically walk the list of objects before the function and after the function, and then you know what is being leaked, which helps you know what actually is being, like where are you screwing up, because if you can see the object, then you can know. But that is not by default. You need to compile Python in this mode, which I do all the time when I hunt in ref counts before memory existed.
All right. So like when you're thinking about like reference counting being so problematic, we're talking about how new programming languages not using it, and how you can leak references, and how like there's owned and borrowed and whatnot. So what would even be any advantages of you doing it like that and not having a different memory management scheme?
Well, I mean, it's very simple to implement. That's one. You don't have a clear ownership model, which that's not technically a problem. Well, I mean, not all the time. But one of the biggest one is that it's deterministic. Like the structure is deterministic until you have a garbage collector, in which case it's not. But like,
Well, yes, like unless you have cycles, like if there were no cycles in references, then there will be no problem. Yes, like but without them, it is deterministic. And what we mean by that is that you can count on Python to free memory, not at some moment in the future, but literally when a scope is being destroyed. So when you're calling a function, there's going to be a local scope for this function to have its locals in. As soon as this function finishes executing, the locals that are there without any other references are going to be cleared out right away.
Right.
Like right away. which is pretty cool.
And people rely on that.
Yes, it's a big reason why PyPy doesn't have more adoption.
Right.
Like when we were testing PyPy at Instagram back in the day, like, what was it, like 2016 or something, the kind of unbounded memory consumption was the biggest blocker, because in CPython, you know that after a function finishes, whatever memory it was using, it goes away right away. In PyPy, there is no reference counting, there's only garbage collection. So in this time that you don't run the garbage collection, which will be like a second or so, like it's not very long,
right?
But in that time, you can gather a ton of memory, you can create a ton of objects. And if you don't program in a way to avoid this, to avoid creating too much, you're going to run out of memory. And that's what happened at the time. So actually, this is a big advantage of ref counting, that you can sort of depend on the fact that it cleans up after itself pretty quickly.
Right. The classic example of this is that data scientists adding two NumPy arrays, which are half the RAM, and then they return. Like the addition, right? You in theory need 3 times the memory of an array in CPython, but in PyPy or if you rely on garbage collector, then you may need much more, because like those are not going to be clean after the function finishes.
Right. But there's also disadvantages of reference counting. So the one that you probably already sort of expect, it's the biggest one, is that there's large overhead, because we're doing this +1, -1, +1, +1, -1, -1 all the time.
Right.
So the overhead is actually pretty significant. We see it all the time. Like, so this eager memory management is almost too eager. 80% of reference count operations occur in the interpreter, says Mark Shannon, mostly to maintain the correct ref count for refs in locals and the eval stack.
And that is technically useless if you think about it.
Yes.
Like when you call a function, with the first thing the function used to do before optimizations was to increase the reference count of the locals when they push it to the stack, right? Because who knows, maybe something takes you away. But if you're in a function, like the caller is certainly keeping that alive. So that increase at the function call, the function start, and that decrease at the function end, that's redundant. Like you don't need that. Like the caller is keeping that alive, right? And sometimes you get like this increase, decrease, like just one after the other. Just because the algorithm is made out of chunks, and when you put all the chunks together, all the bytecode, basically, you get with these operations that technically do nothing. It's just that you didn't code the whole thing in one go. Like you coded like one instruction and then the next instruction, and then when you put those together, it's pretty obvious that it's stupid. But like that's why Mark Shannon wants to fix this doing a technique called abstract interpretation. So the idea is that the idea from like 7,000 meters, right? But you will have a very like an abstract pass of the execution. So you don't really execute the bytecode, but you kind of like will look at the bytecode as a whole, and you will realize that you have a bunch of redundant operations. Some of them will be reference count, but also you will discover that some of them will be other things that you can remove. For instance, setting the instruction pointer, like that, like basically setting which instruction is being executed. Sometimes you don't need that, because like you will remove instructions, or you can prove that the bytecode is not going to change because you're in a loop of a certain size or whatever. So that abstract interpretation will allow you to remove. And also, like one of the first ideas that Sandgross had was precisely to get rid of those stack refs count, because like the caller keeps you alive, so you don't technically need the increase and decrease.
Yeah, and then there's also too much stuff being kept alive, right? Like there is many cases in which you create a reference cycle. We already mentioned that, but there's just a lot of regular end user code that ends up creating reference cycles. Like the kind of classic example is when you have some tree structure and you want to be able to traverse it both ways. And at some point, like you have, classically, you just look at the parent. So like, like any leaf can look at its parent, and you go up and there's a root. But at some point, you also want to be able to traverse children without having this awkward API, which very often creates two-directional references.
Exactly. And by the way, everything there is a balance, because a lot of people laugh at juniors that do this, and they say, oh, your parent nodes should have been a weak ref. You're stupid or whatever. No, well, yes and no. Yes, in the terms like, okay, that avoids cycles. Okay. But also that involves a lot of overhead on the destruction, because like, there is a callback that triggers the destruction of that reference, and it needs to keep like at least 2 objects alive for that node instead of 1. So, it's substantially like there is a non-trivial overhead. So you are going to have a 3 million like 3 node tree, like then depending on what is your performance appetite, you want the stupid version and then call in the garbage collector yourself or not, right?
Yeah, so reference cycles are in fact a big issue, and this is why our cyclic garbage collection is being used. We're going to be talking about that in the next episode, where you've been waiting for that for quite a while, so let's hope it's not going to be in March.
No, February is fine.
Yeah, but it gets worse. Right? Like it's not the end of the disadvantages of reference counting.
Well, the classic one is multiple threads. That's the classic one. Because it's a number, and if you change the number into threads at the same time, then all weird things can happen. Because even if it's a number, there is like 64 bits in the number. So, like some thread can change half of them and some other thread can change some of them. Or like it can get the value in the cache and then they set it at the same time. So instead of increasing by 2, they increase by 1.
We literally had a counter that didn't count properly in Python at some point because of pre-threading. So yes, like counting is not trivial when you have multiple threads, and reference counting is not any exception there.
Right, and that's partially why removing the galore interpret lock is hard. This is just, you will need to change that.
Oh yes, exactly.
Yeah, cool. And also, one of the problems as well, one of the biggest problems I will say for maintaining CPython, now that we have it and we don't have a choice, is that it's very easy to screw up. Like you will say like any form of manual memory management. That's why I laugh when the White House says, "Oh, Python is memory safe." It's like, haha. I mean, maybe for you, but like not for me. But apparently that's fine because like Rust will just say, "Oh, yeah, Rust is memory safe," right? But like probably Rust developer will say, "Well, for you," but like this description is made for end users and assuming there is no bugs. So obviously if there is bugs in the interpreter, that's a bug. It's not the language,
right? That
but
makes sense.
For a CPython core developer that is a wazoo, like that doesn't exist, it's a wazi, it is in the air, and it's very easy to screw up. For instance, a classic mistake, look for it if you want to contribute to CPython or you do C extension, is to mishandle borrow references. Classic move, someone calls PyDig get item, and then you put that somewhere, and you forget to increase the reference count. No.
And it disappears at some moment in time in the future, and it's very confusing when, and you don't know why.
And it's really confusing because, when you don't have ownership, like classic, you call PyDig get item and you put it into a tuple. The tuple steals the reference from the dictionary. So what happens there is that the object gets destroyed. And then in your best scenario, you try to access the object and then you blow up because it's null or 0 or whatever. But in the worst scenario, then the memory allocator will say, "Cool, nobody's using this memory location. It will be cool to put something else." And then you have a tuple with some other dude. Like, "Hey, what's up?"
Yes.
It's like, "You're not a number, no? No, I'm a string. What's up?" I think Brad had one of these like long ago when he was chasing some weird shit in code objects where the code locals. Like the locals array of the code objects.
Yes.
No, sorry, of frames. The locals array of frames or something like that magically became a set. Like for no reason, it's like now it's a set which doesn't contain the locals. It contains something else, like like copyright or something like that. It's like what the fuck is this? So yes, that is very annoying. That's why in debug mode, the memory allocator is really reluctant to reuse memory. It normally tries to use something else and then it puts a bunch of zeros. So you are lucky, but it's still you can still reuse it. So
yeah, but the reason why this is happening, we explained like in episode 16, which is we have our own arenas and we're trying not to ask the operating system for new memory all the time,
right,
and give it back all the time,
because that's
stupid.
Which, by the way, is also every now and again a source of confusion for Python users.
Everybody, everybody. This is the most common issue of memory that is not an issue.
Yeah.
It's someone saying, "Hey, why the residence size of my process is increasing if I remove the objects.
Exactly.
We have a documentation item for this in memory, but obviously people don't read it.
Like it was even worse in Python 2. Like Python 2.5 had like a very particularly gnarly way of like growing the size of the PyMalloc arenas and never giving it back to the operating system. So in theory, like, oh, you had so much free memory for more Python things in your Python process, but those were the times where you literally had only hundreds of megabytes of RAM on your servers. So this was really painful. I debugged a lot of cases where, we need to force Python somehow to actually shrink the size, and you could compile it so that it could like allocate less and not double in the size every time like it needed more, and so on and so on.
There is also a secret function that you can call to get the stats from the allocator. Get the bugmalloc stats in sys. I think it has an underscore in the beginning.
That's cool.
Another classic problem that you can have is the leak. We already discussed this. Like, it's a reference, you forget the decref, and then you get a leak where I don't know. Maybe if someone didn't delete the only below the interpreter, I will tell you where. Like, that would be easy. But now we just know that there is a leak, and that's it. I mean, it takes like some time to fix. But there is also problems. Like, for instance, you can get circular references. And you will say, but Pablo, that's not a problem. You have a garbage collector that you maintain, actually. And the answer is yes, but there still is a problem. Because why? Because like people don't understand exactly how cycles are being made and what operations create cycles. For example, raising an exception creates cycles.
Which is why when you have a named exception in a try except block, that's the sort of tricky scoping rule there.
The as-e.
Yeah, you have like a variable that is being actively deleted by Python after exiting this block. It's not a separate scope. You're still in the same scope, but if you name the exception like
exception as e, right? Like that.
Yes, e. Yes, as e. Like that e does not exist after the block. Like it is literally removed by Python so that we don't have this issue.
Exactly. If you check the bytecode, you will see the del. There's a del bytecode. And it's pretty funny because it used to be that if you run the AST and parse, you will get the del. Like in the because you will see the thing and you will say, of course. But now it's in the compiler, so that happens on the bytecode generation, not on the IST.
Right. But probably the weirdest thing about circular references being handled by the garbage collector is that destruction is now no longer trivial. Like, we're going to talk about this next time, but for now, it's just important to mention that it resolves at some future time. So because it's no longer deterministic, it looks just confusing to the end user.
This is probably 20% of my job at my company.
Really?
Like, it's not so in my company, Bloomberg, we have this thing when like we really recommend people not to do C extensions.
Yeah.
And it's very difficult because it used to be a C++ company, and you know what C++ programmers like to say? I'm very smart. I know how to do C++ in inferior languages like Python. And you know what happens? It blows up because people are wrapping C++, and C++ has deterministic destruction. In C++, you control exactly when things get, mostly exactly, when things get destroyed, but not in Python. So if you, as many people like, to put weird and funky like ownership models, like for instance, classic, at Bloomberg at least, you have a session object or something like that, right? And the session can create like childs, like, I don't know, connection or something, whatever, right? Yeah. And then there is a rule that says all the connections must be destroyed before the session, right? Like all childs must be destroyed before the parent. Like that's a rule. Otherwise it blows up. Why? I don't know, like performance or something. And then in Python, it's literally impossible to guarantee. Like you cannot guarantee it. I mean, it's possible, but like it's just insane. Because like what happens if you raise an exception and then the childs get in like a global list or something like that, and then the garbage collector removes the session and the children at the same time? Because you know what? We will see it next episode. Garbage collection destruction is
not deterministic.
Wow, which means that the order of destruction is undefined. Well, it's defined if you maintain the garbage collector, but I will tell you what is the real order.
Yeah, but it depends on even code that is being executed during the destruction.
Yes.
Because you can resurrect things.
You can change the order. I'm not going to say publicly how. But yes, it has to be with references. But I won't tell you which is the secret. Well, anyway,
right.
And that makes it impossible. And everybody gets this wrong. Like everybody. You know what happens? Like locks. Oh, your object has a lock, and another object has a lock, and it does a bunch of locking destruction, and both objects gets into the GC in a cycle, and then the garbage collector removes in weird orders and locks, deadlock. Classic. Deadlocks at GC time, mega common, super common, because but so don't wrap in Python is hard. Don't wrap Python if you're a C++ programmer. Just do a C++ like service or something, and then just talk to it, like just with the wire. Much easier, because it will go to you and to your children at night. It will do it. It will wear a mask of the garbage collector, and it will scare you to shit. So don't do it. Don't wrap C++ in Python. Just don't. Leave it to the professionals. Yes, that's what you should do. Yeah. Okay. And the other one, just for completion, is a double free, which you say, well, I mean, that can happen in any language. Yes, but in Python it's even more annoying, because the double free can happen delayed. Oh no, what do you mean? Well, I mean, you decrease 2 times, like below 0. If you are in debug mode, then you get a nasty error, like, double free. So that's nice. But you get into a production version, like you get nothing. So maybe you crash, maybe you don't. But you don't know when it happens.
Yeah, and the double free is sort of like easy to explain, but when you actually have a case of this, usually it's not trivial to see right away. Because what is typically the problem is when you have kind of complicated control flow.
Right.
So like classic cases of this is with error handling, where kind of you have something that has to execute finally. So in C, there's no try finally. There's no easy way to say that, like, doesn't matter how I got here, you should actually execute that bit as well, which is why one of those things like unsafe in Rust, in C, everybody's like, oh, don't program with gotos. Gotos are terrible. But like C code of Python is full of gotos. And those are actually very well structured and not a smell. Like, we actually like those because those allow us to have this model of try finally, where we're doing a thing and then, oh, okay, it failed, go to error. And there's one nice place in which we do all error handling. And that way we minimize the cases of freeing something twice or leaking it if you don't do enough of freeing.
Do you know that C, the illegal language, only GNU, like GCC, has destructors?
Really?
Yes, it has something called, it's a obviously non-portable thing, only GNU, but other thing supported is called cleanup callbacks. So you can attach a cleanup callback to an object, and it will call it when the scope finishes, literally the destructor.
Interesting.
Yes. Yes, but it's obviously not portable. And it looks a bit funky, but it's typically used internally in GNU, especially for files, like classic close file, if function returns something like that. But yeah, it's called, it uses one of these underscore attribute. So it's under attribute cleanup.
So glibc uses that?
Yes, and you can use it as well if you use GCC.
Yeah, so because reference counts are not really that cool, right?
Right, exactly.
There's very many ways in which we can avoid actually doing the reference counting. And historically, Python didn't do much of that, but it did intern strings, which meant if you have some strings that are used very many times in your program, then you're going to just pre-allocate them, which saves memory and the time to allocate, but also that's what you actually save, which is this reference counting +1 -1, which you have an empty string or a single character,
right?
Or some identifiers. Literally there is an alphabet in the source code of Python that says whether the string applies for interning or not. My hope initially was for the now infamous PEP 563 to also be a performance optimization because of string interning. We never actually did grow the alphabet for string interning to include the square brackets, which very many type annotations have, which causes those strings to not be interned actually. But many are. So if you have like a bad example of a string like Pablo, yes, that thing will will intern. So that thing actually will not cause like reference counting to the same extent as a string with Łukasz in it, because
that's evil. That's fuck up.
Is not a C identifier. It is a valid Python identifier, but it's not a valid C identifier. So no, that will not work.
This is strings.
Yeah.
But we also have some other optimizations for avoiding reference counting. I think the most famous one right now is PEP 683, Immortal Objects. And the whole scenario, I mean, it has several takes, like, try to make life easier for some interpreters and whatnot. But one of the most interesting things, for instance, is that for performance, is that there is a bunch of objects that are kind of always there, like none, like nobody's going to remove none, right? So like, why are you increasing reference count on none if it's not going to go away, or true, or false, or many other things? So the PAP, proposes, well, I mean, it's accepted, so we already have it. But you can set a bunch of bits in the reference count, so that's why you get these insanely big reference counts, because it's really that high bit set. And that means that basically means, okay, this object is immortal, don't touch it. And because you don't touch it, then you avoid the reference count, which has other consequences. By the way, one of the consequences, even if it's not on the secret script that nobody can see, is that reference count has one very big problem that Łukasz knows a lot about, which is that is really the biggest enemy of copy on write. Chun, chun, chun.
Yes.
Tell us about that, Łukasz, very quickly.
Okay, so certain operating systems like Linux allow you to fork processes. What fork is doing is when you issue this system call, it copies your process into a child process and lets you know that now there is a child. You can actually check whether you are the child or you are the parent. The reason you have to check whether you're the child is that your child process actually starts from the same moment of execution, at least in theory, as the parent, and it can continue running as if it was a perfect copy of what happened in the parent. So now, fantastic, you can have a parallel computation of whatever you were doing before, and you can use the fact that there's imports that you already did, and some setup that you already did, and some global state that you already shared. So sounds great. Like, I honestly don't really think you should be using this. The reason why is that forking and threading creates a lot of edge casey issues that are terrible to debug.
Right.
Plus, forking without resetting the state of the process causes certain issues with locks and so on, where you can have the child process hold a lock that it was not aware it was holding, and then there's deadlock. So you shouldn't really be using this, but we are in the real world and people are. So Linux had this idea for an optimization. What you can do is, instead of actually doing the copy that I told you about, you can just reuse the same memory of the parent process, as long as neither the parent nor the child wrote something new to it. But unfortunately, all of this optimization is nullified by Python, where even reading memory causes writes to the memory, and passing data, even if you're not mutating it, causes reference counts to increase and decrease, which sort of nullifies this entire optimization.
Not only on the object you write or read, because it's the same, but also on all the other memory that is in the same page, because this optimization applies on like at the level of system pages. So like the operative system like Linux normally has like this concept of memory pages, which are normally 4K, and like when you touch that page, it will copy the entire page. So not just the tiny object that you touch, but everything else that is there.
Right. So like for this reason, and we're sort of skipping ahead to the next episode, like Instagram proposed an API that is now part of Python, which was to freeze the memory of a process and just say like everything to that point, just treat this as effectively immortal, freeze it. Just don't care about like ever reclaiming this. And that was mostly for garbage collection. But now we are extending this to actually mean like if objects are immortal, we're not even caring about their reference counts. We're not doing anything with them. Only there is a hilarious open issue on CPython, which is literally called Immortal with scary quotes, right? With air quotes, objects aren't immortal. And that breaks things. It is about the fact that like, in many cases, things that you think will never gonna be destroyed, there are cases in which they are in fact cleaned and a new one is created, and this causes problems. So now there is the detection of that, and there's a kind of ongoing investigation to make sure that we're actually never breaking this invariant that an immortal object should live forever, where forever stands for how long the process lives.
Yes. More in the garbage collector episode. Very exciting. And I mean, we could go into more details, but we are already like an hour and something. And we have a very big, interesting section of a lot of goodies for the new version of Python to talk about. So let's switch to that. Let's switch to
what's
going on
in CPython. Wow, we need to start with personal changes. So personal changes because we had a steering council election.
Steering council.
Right. Yes. And we're saying goodbye to Thomas Wouters, and we are saying hello to Dong Hee Na from South Korea, who is a new member of the steering council. So that's pretty cool.
It makes the meetings happen at interesting hours, because now we have European members like me and US members like mostly everyone else, and now we have Dong Hee. So yeah, the time zones are amazing.
Honestly, I enjoy this. I personally think it's perfect because of all this time zone shenanigans. For whatever reason, I never got the invite to those meetings.
We are still figuring it out. Don't worry, you will appear at 1 a.m. Sometime. You will suffer it.
Okay, so there's gonna be like meetings every week to kind of cover for the ones that did not happen.
No, but like you will see. So I'm not spoiling it for you. You will see what happens. So it's going to be an experience this year. But yes,
it's gonna be interesting.
Very cool.
We also grew a new core developer.
Yes, Benedict Tran, which was mentored by Victor Stinner, our very good friend, and they are basically just rocking across the repository. Lots of contributions.
Right. So now we have a few groups of things that happened in CPython in terms of code changes. And there are a few small groups and one gigantic group that's really like, I think, wow, like there is motion in many ways in Python, in many areas of Python, but in particularly one, there is, I think, the most. So let's start with others, I guess.
Features.
Yeah, like there's features. Okay, so speaking of our friend Victor Stinner, he spearheaded PEP 757, Pylong Import and Export API. So he produced a PR to actually expose this in July, and that was reviewed forever and finally landed recently. So now this is actually done and landing in Python 3.14,
which is awesome. And like, by the way, this is quite hard because like this PEP and many of the changes are quite tricky and requires a lot of rewriting. So Victor has pulled through. So just all our respect to Victor pulling this. So it's very important work. It's normally hidden. And
we're also very sorry for him, like already, because all of this hard work that is actually like technical work and whatnot is going to be entirely not visible to end users. But things that are going to be visible for end users are going to be like colors in places where there were no colors before.
Wow.
So things that we sort of spearheaded with PyRepo, now there's going to be color and unit test. So Hugo van Kemenade added this.
Yes, which is awesome.
So now Yeah, like the reports of unit tests are colored. Whether it's red or green is up to you, but there's going to be color.
Yes, I love this change every time I see it. Awesome. Now we get to
Interesting changes.
the first change that we have here is some get opt and opt parse now are undeprecated. Undeprecated as a change by Elisa Coughlin. And why they got undeprecated, Gukesh?
Yeah, because click is based on opt parse and not arc parse, because opt parse was easier to extend and less opinionated. So there was always a kind of worry that like, how can one of the most popular packages for Python be based on something that is deprecated and might get removed from Python in a future version? So first of all, like if it was, then it would just be bundled in a future version of Click. So not really a big deal, honestly. But still, it was weird that like this kind of technology of the future is based on technology that is like deprecated. But really, the deprecation was, I think, aspirational at the time that arc parse was added. So the reality of the situation was like now like rectified, and like Alyssa Coughlin said, like, hey, this is actually never going away. Like there's no danger of us ever removing opt parse. So why say that it's deprecated? And get opt is in an even kind of more, I don't know, natural position there, because nobody in their right mind will use get opt for new programs right now if they are starting them from scratch as Python programs. But get opt is in fact like a one-to-one translation of the API that you have in C.
Right.
So if for whatever reason you are recreating a tool that has its origin in C, you will want the behavior to be exactly the same, and this is how you get there. So, kind of, again, we're not going to be removing this. It's going to stay there. So, undeprecated.
Undeprecated. Very cool. One very cool change that I really like is that Edith, so she made some new internal docs about the Git compilation, which are really good. Like she has been doing a lot of like doc refactoring around.
Yes.
In particular, in the dep guide, now we have all the changes for internal documentations in the CPython repo, and the guide is kind of pulling them in, which is cool because now you get version changes. So if you go to the 3.8, 3.9 or 10 or whatever, you will see the design for that version, not the design for the last one.
That makes perfect sense to me.
And there is all sorts of interesting information about like bytecode families and whatnot. So if you want to know how the Git works, very good documentation.
Yeah, that's very cool. Barney Gale is working on PathLab recently. So one thing that I noticed is like his work on ABCs with runtime checkable protocols. So far, they are private, so mostly for the ability for PathLab to be like, kind of factored more nicely. But one of the things that like the consequences that the changes already have is that like if you are creating your own subclasses of paths, they're going to be able to do more compared to before, since the internal machinery of PathLab will recognize that the subclasses that you're having like are more capable and based on the POSIX paths, which is what most people actually want. But the ABCs actually look interesting since they allow you to use type checking both in a static way and also to have like the runtime checkable protocol. So I don't know, like maybe we're gonna get them in 3.14, but I don't want to actually maybe spoil the show, because we were talking about like Scander being added as an API on PathLab some episodes ago, and now this is removed because it turned out that like what should actually happen is this thing should be like a implementation detail of other APIs that are already there and not exposed directly, since it was exposing OS, their entry, which is different from the PathLab's path object, but similar enough that it was confusing. There is an entire issue about those like, kind of design considerations. So I don't want to be like, in any way complicating Barney's work. I'm just saying like, I like those ABCs. So yeah.
Hopefully we get them for 3.14. One very cool change as well, which was surprisingly short for what I thought initially it was going to be, is that now any warning that are raised during our test suite, the CPython test suite, are treated as errors. which is a very good change because like a lot of things that weren't supposed to happen raise warnings and we didn't know about them.
Yes.
This is the kind of change that you will know that is dead by 1,000 cuts. Because I need to fix all the warnings that were there.
But this is good. You know why this is good? Not because like, oh, there's a warning on my test, so I should fix it. No, because usually the way those warnings are introduced is that somebody is making a sweeping change, and that is raising warnings all over the place. And now, well, unfortunately for them, but fortunately for everybody else, this sort of pushes the, responsibility for keeping the regression test suite clean to the person that makes the change.
And is showing up errors. Like one of the changes that so the change actually just changed the warning level to from default to error, right? And we fixed a bunch of things. One of the biggest things is PyRepl. We have a test in PyRepl that it was not using a context manager for temp file named temporary file, so that the destruction was like being raised.
I don't know who wrote that, probably me.
I don't know. I think it's a contributor. Let's say that. Let's say it's a contributor. Like, what about that?
It's an unnamed contributor.
Exactly. maybe Polish contributor. But yes, and I think like also test socket is still raising warnings because apparently that was insane.
Yes, that's the one thing where like it's gonna be hard like to actually just
Okay.
So Hood Chatham, our good friend, mathematician, and a maintainer of Pyodide,
awesome person,
is on a quest for Python to work better on mscripting. Is that related to Pyodide? Probably. But what he wants is for Python to support the JavaScript promise integration. So JSPI, there's a spec, and it's sort of evolving. It's already like on version 4, I think, or so on. And it's making like kind of things a little hard for WebAssembly runtimes like Pyodide. But like just reading through how Hood is finding ways to actually progress with it. It's pretty cool. Like in particular, there's some ingenious ways to discover how like you can read JavaScript function signatures using the WebAssembly garbage collector.
That is insane.
And have you read this?
Yes,
it's not actually a nice API on the garbage collector saying like read function signature. No, you're just using the fact that they are being tracked by the garbage collector.
Yes.
And there's a way for you to just read some data structure that's like, oh, this is not part of the spec, but every implementer of the spec has this. So I guess we can use this. But yeah, like this is pretty cool because this will actually make usage of Pyodide in the browser better. I'm like lately like really into that. So like, I'm all into better interoperability with JavaScript. If you are not in that world, what you probably don't understand right now, which I didn't until very recently, is like, what do you mean like this sort of interop with JavaScript? What is going on? So in a web browser, there are two worlds. There is WebAssembly where like everything is sort of like democracy, right? You can write Rust and compile to WebAssembly. You can write Python and run it on WebAssembly. And then this Python running on WebAssembly can access memory that another WebAssembly thing created. And it can mutate that memory, like everything is sort of democratic. And then there's this JavaScript world that predates all of WebAssembly. So this one is special. It has its way to like read USB directly, right? To do like access your camera and do like a bunch of stuff on your operating system. So this JavaScript world is separated from WebAssembly. You cannot directly mutate memory on there. You cannot read a lot of this memory unless there are APIs for it and so on and so on. For a ton of things, you have to copy things and kind of awkwardly just interact with this world as a foreign function interface, essentially. So this change that Hood is working on is allowing us to like be more efficient and kind of complete and make more transparent interop. Because what you want is to support like APIs that feel as if you are writing Python from our site and so on and so on. And like for the stack traces to make more sense. So like this is a big part of that. And like one of the kind of related, hard to tell changes that Hood is also working on is C-types is now actually supported on mscripting, which is an impressive feat.
Right. And the last thing that we have in the interesting section is a fun, obscure bug fix that Peter Victorin made. Basically, this was a bug on the like the cache, the bytecode caches for certain operations like get attribute and whatnot. And this is when you have incompatible MRO entries. So if you have like a class and then you use like an instance of that in a function or something like that, we use the new caches of the interpreter to basically not do the lookup all the time if we can prove that we know for a fact that nobody has changed the actual attribute, right? So instead of going again through the MRO and blah blah blah, like we just get the value directly from the place. But I think it was some gross that open a bug that you create like some weird meta class, like a class that inherits from a weird meta class that has its own MRO, and then you start mutating that, like that alters the MRO, and therefore you should invalidate the cache, but we will not invalidate in the cache. So there is this function in theory that it recomputes the MRO and tells the cache if it should be invalidated, but it was broken since 3.10. I mean, for a weird use case, but anyway, the thing is that you're getting the wrong value, and that is fixed by Peter.
Cool.
So performance. We have a bunch of things. So we can probably group a bunch with proper attribution.
Yeah, Mark Shannon working on instrumenting for_iter better so that there's fewer instruction dispatches and there's better jitting. So
better jitting.
Yeah, that's what we want.
More
also, Mark Shannon did the removal of conditional stack effects from bytecodes.c.
Dude, I love this because like in frame object.c, like the guts of the frame object, there is like a stupid function that has some weird conditionals, really, really difficult to read, that depends on like the number of the instruction, and like those variables are called j. If j is less than 3, then do this, and like has a different stack effect. So that code was, I always was like super scared to look at that, and now it's gone because he still has variant bytecode effects. So like a instruction can have 1, 2, 3 variables in the stack or something like that, depending on stuff. Yeah. But conditional, depending on like the value or something like that, like is the value known, then put 3. Like that is gone, which is great.
Very cool. All right. And then Benedict Tran, our newest core developer, did a bunch of performance optimizations, mostly around import time, but also to make fnmatch.translate faster. That is cool. And the import time improvements are in base 64, pickle, CSV, and a contributor, Taneli Hukinen, did tomolib import time improvements by just upstreaming what the maintainers there did. A lot of those are just guarding import typing imports so that is faster, but also some like initialization of caches and stuff like, oh, we only use this regular expression to do something that we could just as well just do with string.
Right, move the import.
Yeah, so like this sort of thing. But like what that causes is for the graph of imports to become kind of flatter when you're importing a larger program.
Right.
Because, if you have a program big enough, you're going to import everything anyway, because you're going to have like enough of third-party libraries. So that for those, it doesn't matter. But for the smaller command line tools that have like subcommands for stuff, what we want to achieve is for --help of those tools to be really quick. Because --help probably shouldn't be importing all of your libraries. That should be doable without the full scan of like all of your code base. So for those things, the kind of golf game of what should be important and what shouldn't like actually makes sense. So that's pretty good work.
Right. Now we go to our favorite section, the big chungus, which is free threading.
Yes, we have the most for this. And I was wondering whether I should be really calling it free threading or thread safety, because a ton of those changes is thread safety, but it turns out that actually most of them are not. So yeah, this is free threading.
Let me start with one of my favorite ones. This is a change by Nel Schumacher. which has added like a marking phase for the free thread cycle GC. So as many of you know, because we mentioned it in other episodes, now we have two versions of the GC.
Yes.
We will cover it more in the next episode probably. One that is free thread and the other that is normal, and they are slightly diverging. And there is some optimizations that were in the previous one that couldn't be ported easily to the new one. So he did basically the same thing. So he added an optimization to the GC that basically it starts basically for known objects that are quote roots. I'm saying quote because in Python there is not really a good concept of roots, but like things that certainly are going to probably be alive and every children is going to be alive. Think like the sys.modules, right? Like the important modules are not going away. So anything that is referred by that will be alive. So it's not really needed to run the GC around that, because that's going to be visiting a lot of objects that we really don't need to know. So that's the marking phase, and he replicated that on the free thread GC. And even if it needs to do a bit of extra work, because the marking phase, the total time is slightly lower, which is slightly lower, which is very good. And that's very nice. I'm very happy to see this change.
Yeah, like you're gonna hear about Neil a bunch of times here in the section on free threading. And he also added logs to the warnings module because, like as Pablo said, like what the warnings module has some global state. And for thread safety of this, like there needed to be more logs than we had before. A lot of those things that are like thread safety fixes at this point are kind of, I would call edge casey, in the case that like they didn't get to Python 3.13 and like the world didn't burn, but at some point in production code you're going to get to those sooner or later. So now like the warnings module is thread safer, at least.
Right.
Some of the things are actually like less of like, things are kind of weird in the cache, but they're downright crashes. Like dnovelent fixed a crash when reading from an object instance dictionary while replacing it. So that's, again, like sounds pretty edge casey, like who would do that? But like in production code, sooner or later, you're going to find this and it's going to happen. And a crash of an interpreter is always tragic. So great that this is fixed.
Right. Then we have some changes by some. The first one is that now the first reference counting now is used also for thread locals, and this this allow the some of the benchmarks that we're using thread locals to scale linearly now with the number, close to linearly with the number of threads. And this is because if you don't activate the first reference count, we know that many of these things will not benefit from the speedups of multiple threads.
Yeah, if you're wondering why we didn't really cover different reference counting right now, is because ironically, it is very tied to the garbage collector. So we're going to be talking about this next time. Right.
The other change that is also tied to the garbage collector is that object resurrection is now thread safe. Object resurrection is always very annoying. And this was more annoying because the thread safety aspect of it, but now this is thread safe. We will cover more this in detail in the next episode.
Yeah.
But yeah, thanks to Sam to fix this.
Yeah, so Sam did like quite a few other changes, like improving performance by 2% by simplifying PyStackRef from PyObject steal. Like it's one of those things where the change itself is sort of very limited. Like you can see where it is, and it's surprising how big of an impact it has on the overall behavior of the runtime.
Right. One of the changes that I have laughed quite a lot for stupid reasons is that Sam Gross changed, so added some missing locks in the list object implementation, which you will say, well, at this time, list objects will be thread safe. But the reason I laugh a lot is because in the diff of this PR, if I remember, there is actually, let me look at, yes, there is my favorite stupid function name, which is list _ as _ subcrease log health. I don't know. I'm just a kid. So list as is the as of the list. I mean, locked now. So thanks Sam to add logs to the as of the list. Yeah, and another interesting change that we have from Peter Bierma.
When you are setting the recursion limit, we really need to stop the world, right? Because you cannot just do this locally, like, right? Yeah. So like that was one of those things where like it's sort of you understand it while you hear, like after you hear it, but just nobody actually, kind of thought about it before. Yeah, and like Peter made a ton of changes, honestly, in free threading. So per object memory access, now is synchronized in C types. And this is important because now, again, that's thread safe. So cool. And there is a list used now for @exit callbacks, because before, without them, if you have multiple threads, you would have segfaults. So like all those sorts of changes are like super important to make sure that free threading is going to be usable in the real world. So Peter Bierma, great work.
Right. Then we have a change by Edward Shu, which is that memory view export had a race condition that now is fixed.
Yeah. And then there is a big group of changes that fix, like a design limitation of the free-threaded Python in 3.13. So in 3.14, a lot of missing functionality of Python is going to be restored in the free threading build. And the most important thing is the specialized interpreter. So to make that work, a lot of those specializations need to be made thread safe, but in a way that doesn't make specialization kind of too slow. Because otherwise, if it makes it too slow to even consider specialization, then you are defeating the purpose.
Right.
So this is tricky work. And again, Neil Schemenauer did great here. So store_adder and send were made compatible with the free thread specialization by Neil. Matt Page did load global and call. Dong Hina, the newest steering council member, did to_bool, because non-bool int and strings are immutable. So it was safe in a pretty efficient way to add specializations to those. So that was a good discovery. And then the binary subscript get item is also now specialized as well. So free threading in Python 3.14 is going to become less of a snail compared to Python 3.13.
Another change by Don He was that by ASCII objects now handle intern fields using atomic operations. So also,
yeah, very cool.
Right.
And the steering council member that Dong Hina replaced, what is he doing now? Where is he? What, what's up with him?
He's swimming now in the ocean.
No, was also adding free-threaded specializations. Thomas Wouters added compare_op as a free-threaded specialization. So that's pretty cool.
And then we have Kirill Podropigora added also free-threaded specialization for unpack sequence, quite common for tuple unpacking. And also we have Kumar, our core developer, was promoted last year as well. So he added, normally he works in AsyncIO, but he's also working in other places. And here we can see that he added free-threaded data. He fixed a free-threaded data race in PyUnicode as utifate and size, which is used all over the place. So I'm pretty happy this is actually fixed.
Yeah, but a lot of Kumar's work is indeed in AsyncIO, and in the intersection of in AsyncIO and free threading. There were very many thread safety issues fixed by Kumar in AsyncIO, and also all_tasks is now safe with concurrent deallocations. There are new thread safety tests for AsyncIO. So I might just as well continue talking about AsyncIO because there were just so many things that Kumar lately added and worked on in AsyncIO. It's just kind of amazing. One of the things that you might be a little worried that Kumar worked on, but actually is a good thing, is that there was an early design in AsyncIO that allowed you to replace the event loop used by AsyncIO by this sort of clunky policy system where you had to create a bunch of classes just so that there was a better policy for an event loop, and then whenever you asked for get event loop or set event loop, it would use this policies implementation and so on and so on. All of the actual alternative event loops didn't really want to work within that system, and it was pretty clunky, and both by the user and by the implementers required to be pretty careful about what you're doing.
Right.
So this is being now deprecated. UV loop has a much easier to use .install function on the module, and a bunch of others just plug in a very similar way. So those policies are not really required for anything. In Python 3.14, you're going to get a deprecation that like, hey, like you don't want to use those policies anymore. If you use UV loop and so on, you're not going to get any deprecation. You are already in the future.
Right.
But if you have some internal company code that actually uses those policies, you're going to get a warning in 3.14, in 3.15, and in 3.16. No code is going to be removed, but those kind of custom policies are not going to be taken into account anymore. Like the get event loop and everything else, like it's also being deprecated and so on. But the entire point is that the policies are not going to actually influence anything anymore. So this is gonna simplify things, I think. Like that was one of those things where I saw it sort of as a Java-esque API. It was sort of kind of class heavy. It didn't really look very Pythonic to me when it was first introduced.
Right. And like another person that is working quite a lot on AsyncIO is Thomas Granger. Quite a lot of changes. One of my favorite ones, by the way, because this is a pattern that a lot of people find very confusing and it's very cool. So he fixed a bunch of, fix is an interesting verb, but like I suppose like it is fixed. He fixed a bunch of reference cycles, like, which again, I know incorrect, it's just that they're obviously slow down things a lot when using eager task creation. And the interesting pattern here, by the way, I don't know you have seen it, in particular, is again exceptions, right? Because like tasks have exceptions, and exception has tracebacks, and traceback have like the base class, and that has the task somewhere. So that was the thing, right? But one of the patterns that is very funky, and I really like that he used, is that normally you will just return the task, right? And the task now I have this reference cycle, because when you return the task itself points to the locals of the functions where you just return. So it points to itself, right? So the pattern is that you do a try, you return the task, but then you do a finally that removes the name task. So like before actually returning from the function, yes, there is a reference from the task to the local scope of the function when you're returning the task, but you're removing the name. So the cycle is broken.
Yeah.
That is very cool.
It is very cool. Like the kind of thing that I wonder whether people listening now like are familiar with is eager tasks themselves.
All right.
Like this is sort of like a new concept because that was only added in Python 3.12. So what is that even? So the thing is this, like again, it's a kind of like a pragmatic thing to do, which is if you have AsyncIO, everything is asynchronous, right? There's an event loop ruling everything, and you have tasks. There are plenty of cases in which when you are creating a task, like the thing that you wanted to do is already actually done. So if you could actually make a task that is eager, which means when it already has an answer, it's going to be passed right away instead of going through the event loop and running everything else that might have happened on all like networking and other callbacks that are waiting and so on and so on. Instead of that, if you could be eager and just pass what you are returning like straight to what is awaiting on this is going to make things much faster. And the reason why reference cycles were painful there is that if you are relying on eager tasks, then this determinism of reference counts is important. That like you're going to run through memory really quickly if you're going to be adding a bunch of things to be garbage collected a minute later. The entire point of an event loop is that this is a really hot loop. There can be very many things happening within 1 second or so on. So this was really like an impactful fix by Thomas.
Right. Another thing that he fixed is that in eager tasks, like you in AsyncIO you can basically name tasks, and that helps you when you're like those tasks. So in the stack traces or when you inspect the task objects themselves, you bring them. You can have some knowledge of like what the hell is this task, because otherwise you can have something like task object at memory address blah blah blah, and that's not very informative. So in many places in AsyncIO, this is made automatically for you sometimes, but some other times it's still better to have. And he fixed a bug when unfortunately this task couldn't be properly named. So now the name keyword is supported when you call loop.createTask. So you can also pass now a name, and many other places like task group create task and set task factory. Yeah.
Yeah, Thomas also fixed like invalid, sadly, optimization that was leading to missed or incorrect cancellations in eager tasks. So that is handled now. And one of those things that like the name is obvious, but how to use it is not, has much better documentation now. What I'm talking about is run coroutine thread safe. There is this special function where like, okay, you know what it's supposed to do, but how to use it and when not to use it and what to pass, like there were some edge cases always there. Now there is clear examples in the documentation. So for each of those cases that like you might not be kind of, confident in the combination of arguments, there are nice examples right in the docs on how to use this. So Thomas did a ton of work on AsyncIO recently. I'm very happy to see this.
Right. And now, as you are the only one of us that have an actual Windows machine, maybe you can talk about the Windows changes.
Yeah, since they're also arguably 3 out of 4 of them are really PyRepl changes, so why not? But let's start with another one. So recently, we have received a new version of Windows Server. There's Windows Server 2025. So now that is detected in Platform PY, which is cool because soon enough, we're going to get that on GitHub Actions. So it's going to be important for us to differentiate it from the last version, which was 2019. And the PyRepl changes, there's 3 of them. Like one is kind of more general, but PyRepl is a big kind of receiving end of that, which is that console color output can now be forced, like on POSIX. So you had nice environment variables on POSIX for forcing or disallowing color output. Now there is a way to force and disable color output on Windows as well.
This is a change by Andrei Efremov.
Yeah, that's a nice change. And maybe more importantly, PyRepl got better. There are 2 changes. First by Victor Stinner, which is that history is now compatible with Windows, which was a big thing that we missed initially. Like, sorry for that, but like clearly we didn't really pay attention on the fact that like we weren't properly saving the history file since the support for read line there like was inadequate. So Victor fixed this, and now you can remember all the things that you typed in previous sessions on PowerShell and CMD.exe as well. And one of those things that you were doing often was skipping words. So in PyRepl on Mac and Linux, you can use Control with arrows to skip entire words within a line in PyRepl. And that didn't work on Windows, so now that is fixed as well.
Right, and this is a change by Pauli Peña.
Yeah, that's very nice. So yes, Windows better than ever for PyRepl.
Yes, there is a bunch of also open issues on Windows that we need just time to go through. A lot of contribution as well.
Indeed.
Yes, so we need to probably like
sprint on that. Yes.
Yeah. And then we have a big security fix in the email module, and this is fix the email address header folding with long quote strings by Mike Edmonds. So this is, I think it has a CB attached to this.
Oh, fantastic. So soon enough, when we get our backports ready for 3.9 and 3.10, we're going to have another release, I guess.
It doesn't have a CB, but I think it's a violation of the RFC. But yeah, no CB attached, looks like. Yep. Cool.
All right.
And that's all. I mean, it's everything as every single time, especially now that we have 2 months to go. If you don't see your name here, it's not because we hate you, or it's just that there is so many things to talk about that it's very hard to cover. We try to cover the most important ones, like in terms of like size or impact or attention, but it's inevitable that we miss something. So if we have missed something that you think we should include here, please reach to us. We are very friendly, so you can reach to us by email or social networks, whatever you want. And, just feel free to say, hey, people, you missed my thing and it's important. And we will sure to correct it and include it. So,
Exactly right. Yeah. And in the meantime, see you in 2 weeks.
See you in 2 weeks. For real now. For real.